This is an interesting chapter and a pretty short one. It's marked with an asterisk, so it's not mandatory, but it is very interesting as it shows the relationship of the electric field to the gravitational field. When we talked about electric charge and force, we noticed how similar that was to the gravitational force. There is a similar relationship between the electric field and the gravitational field. The reason is it's not just because that's how the universe works, which it is, but they are both central forces, and they both act along the line connecting the objects. So you have a central force, like the planet Earth, generating a gravitational field that other objects feel, and that force is on a straight line between the other object and, in that example, the Earth. There is a key difference between the two fields and forces. Mass, which is the source of the gravitational field, is always positive. The force is always attractive. There's no such thing as anti-gravity. However, charge, which serves as a source for the electric field, can be either negative or positive, and the forces are either attractive, for example, if you have a positive and a minus charge, or repulsive if you have the same charges. Let's review with gravity. Here's the gravitational force, where we have the universal gravitational constant g. We have two masses, and in this case we'll assume the large M represents the mass that we're interested in its gravitational field, and M is some small test mass, sort of like the positive test charge that we talked about in defining the electric field. So what we will do is we will divide both sides of this equation by little m, just like earlier we divided both sides by little q, and you get something that we call G, which is the gravitational field. It's equal to the force divided by the mass, and in this case that will be large G times large M divided by r squared. And we can also find the weight of the mass on a planet by just basically it's this Fg equals mg. You should remember that from first semester physics. So we are now defining G as the gravitational field, which is analogous to this electric field that we just defined in this chapter. This chart summarizes the differences and similarities between the electric field and the gravitational field. Gravity, we started with Newton's law of universal gravitation. For electricity, we started with Coulomb's law. We have the two equations here, which are algebraically exact. We just have different letters in here. Big G here, which is universal gravitational constant, is this value, which is a 10 to the minus 11th type of number, where the electric constant, Coulomb's constant, is 10 to the 9th. This partially reflects how the electric forces are much, much stronger than gravity. The object generating the field for gravity would be mass, which is represented in kilograms, and for electricity, it's charge, which is represented by coulombs. In both cases, the force is dependent on the inverse square of the distance between the centers of mass for gravity and the centers of charge for the electric field. And again, we have the electric field over here, gravitational field here. Gravitational field is little g equals gm over r squared. And of course, on the planet Earth, on the surface, g is equal to 9.8 meters per second squared. That's the same g we've done already. And then the electric field is kq over r squared.